In this video, I want to cover how we classify compounds. This is helpful information because you need to be able to classify the compound that you're looking at in order to determine how to name it. So this is the first step in coming up with names of compounds and then writing formulas for compounds. Before I get into the details on classifying, I just want to review a few key points about how atoms are put together. We'll spend a lot more time on this later, but your atomic structure basically is you have a nucleus at the center of the atom, and your nucleus will contain both protons, which have a positive charge, and neutrons, which are neutral with no charge. We will be talking about how it is the number of protons that determine the identity of the element. So the same number of protons is always found in all atoms of a particular element. Carbon, for example, always have 6 protons. Surrounding that nucleus, we have the electrons. The electrons are in an electron cloud, is usually how we talk about it, though they tend to be drawn in pictures like they're planets going around, orbiting around a sun. Now, electrons can move. They can be pulled from one atom to the other, or they can be shared between two atoms, and that's what makes the chemical bonds that hold these compounds together. So the bonds are all about the electrons, and we'll be talking about bonds in this video. So I just want to remind you that it is what we're talking about is what's happening with the electrons in the various atoms that are in our compounds. Our compounds are written with formulas, and there are certain key things that you need to know about the formulas. First of all, your formulas will contain atomic symbols. Those are the abbreviations for the different element names, and those atomic symbols tell you which atoms are in the compound. An important thing to note is where is the capital letter, because every capital letter will start a new element. Many of our compounds, the atomic symbol is only a capital letter, and then other ones have a capital letter and a small letter to make up the atomic symbol. But every new capital letter will be a new element. And then often there are subscripts or little numbers that are down below the letters in the formula. And subscripts are connected to the atom on the left side of the number. They only pertain to whatever atom they follow. They are directly after. Those subscripts tell you how many of that particular atom that they're connected to are present inside your compound. Sometimes in more complicated compounds you also have parentheses, and there'll be subscripts both inside and outside of that parentheses. The subscripts inside the parentheses just pertain to the atom that they follow, but subscripts outside of the parentheses affect all the atoms inside the parentheses. So you have to sort of factor them in if you want to see how many atoms are present in that compound. So I have some sample compounds here on the bottom. The first one, sodium chloride, familiar table salt. We have 2 atoms, Na representing sodium and Cl representing chloride. If there is no subscript that you can see, it's like in algebra where you have X and you know it's only one X. Well, if we have Na, we know we have one Na. We have one sodium, we have one chloride atom present in our sodium chloride formula. The next formula, MgSO4, contains 3 atoms because you see three types of elements, because you have 3 capital letters. So Mg is your magnesium, S is sulfur, and O is oxygen. And this subscript 4 only pertains to the oxygen. So there are 6 individual atoms in this compound, 1 magnesium, 1 sulfur, and 4 oxygen. And then our more complicated formula on the bottom, copper nitrate. Again, you see we've got a capital C with a U after it. That's our copper atomic symbol. We have a capital N and a capital O. So there are 3 different kinds of elements in this compound. Inside the parentheses, the little 3 subscript applies to the oxygen. So NO3 is the nitrate ion, and we'll talk about what those are later on. And then the parentheses, we have a 2 after the parentheses, so this 2 pertains to everything inside the parentheses. So this tells you that there is a copper atom, and then there are 2 of these NO3 groups of atoms, 2 nitrate groups present in this formula. Remember also we were talking about the introduction to the periodic table. We have big categories where there are metals found primarily on the left side of the periodic table, nonmetals over in the right-hand corner, and then we have metalloids in the middle. For the purpose of classification, really we're just dividing the periodic table into your metals and nonmetals. We're not worried in introductory chemistry about the metalloids and how they fit in. We'll be working with really only about 30, maybe 35 out of the 118 elements that we have on the periodic table. In some cases, that's just practically what we could work with in a classroom laboratory, but also some of these things really just are difficult to obtain. They're only present in very small numbers. They might be radioactive, but we don't want to work at in school. So you do not have to memorize all 118. So compounds can be classified into 3 groups, but we're really going to only focus on 2 of those groups. The first one is when you have a metal atom connected to another metal atom. So a metal plus a metal will form either a pure metal, or which is all like anything else, a pure substance, all one kind of atom, or an alloy. And really most of the things that we see as metal around us are alloys. Alloys are combinations of metals or metals combined with some nonmetal substance. The bonds that hold these metals together are known as metallic bonds. And in these metallic bonds, the electrons really float freely between the different atoms. They're not attached to any one in particular, and this is why metals can be so good at conducting electricity. We're not really going to spend a lot of time working with substances that have metallic bonds, but I just wanted to let you know that this was out there. This is one of the categories. As I said, most of the things that you think of as being metal probably are alloys, combinations of metals, or maybe a metal and something that is another solid. So some of the common alloys that we have, bronze is one example. Bronze has been around since ancient times. You might have heard of the Bronze Age. It's a combination of copper and tin, roughly 90% copper, 10% tin. Those sort of rough numbers. But what this produces is a hard, shiny metal that resists corrosion. So it is harder than copper, it is harder than tin, and it will not rust, it will not break down, so it lasts longer. So that was the advantage of bronze. Brass is another very common alloy. It's made out of copper plus zinc and produces a hard, shiny metal. And many things that you think of as being gold, kind of in everyday life, we've got some golden jewelry over here, or you might have, a doorknob that is golden in color. It's probably brass that's been put on the outside. A thin layer of brass, this combination, this alloy of copper and zinc. Stainless steel is a very, very common alloy, and it's a combination of several things. It has iron plus carbon. That's sort of the basic recipe for steel, iron and carbon. And then we've got some chromium added in there too, I think, to make it nice and shiny. And so that gives you a hard, shiny metal that doesn't rust. And so if you are familiar with iron, you know iron rusts relatively easily, whereas stainless steel does not. So that would be the advantage. This is why we make an alloy instead of using a pure metal, because there are some advantages to it. And then probably what you think of as being aluminum actually is dura-alumin. So this is a durable type of aluminum, made up not only of aluminum but also a little bit of copper and a little bit of magnesium and a little bit of manganese. So it's a combination of several elements, creating, again, a very strong metal, a very lightweight, very useful alloy. Even though we call it metal, it's a metal alloy. Okay, so this is really now going to get into the meat of things. This is what you want to be able to identify compounds as containing metals or nonmetals. So if you look at your formula and you see what's present in this compound is a metal and a nonmetal, then what you have formed is an ionic compound. So metals plus nonmetals make ionic compounds. Ionic compounds are held together by ionic bonds. And in ionic bonds, electrons actually move from one atom to the other. They leave one atom, take away an electron to make that more positively charged, and they are added to the other atom to make it more negatively charged. And charged particles have their own name. They're called ions. And so ionic compounds contain ions, which are held together by ionic bonds. This all fits together. The bond itself actually is based on this idea that opposite charges attract, so that you'll have a positive ion, our sodium chloride example down here, for familiarity. Sodium ion is a positive ion, the chloride ion is a negative ion. Those two connect together in an ionic bond to make an ionic compound. So if you're looking at a formula and you see one part of the formula is coming from the metal side of your periodic table and the other part is coming from the non-metal side of your periodic table, then you have an ionic compound. In comparison, you can have a non-metal plus a non-metal, so the elements are all coming from this non-metal side of your periodic table. This particular combination forms a covalent compound, which has covalent bonds holding it together. Another name for covalent compounds are molecular compounds. And in a covalent compound, electrons are actually shared between atoms. They don't go and leave one and land and stick to another atom, but they are shared between the two. In fact, it's more like fought over. This example of water down below, H2O, the oxygen is saying, no, I want that electron, and hydrogen is saying, no, I want that electron. And as they have this tug of war back and forth with the electron, it holds that molecule together, holds that compound together. So if you're looking at a formula and all you see are nonmetals, you know you have a covalent compound. So here's a quick practice. Are these compounds ionic or covalent? A trick to this is that the metal is always going to, well, nearly always, 99% of the time, if there's a metal, it will be the first thing in the formula. So if you look at the first element in the formula and you see a metal, then you know you have an ionic compound. So the first compound on the list starts off with Al. And that's the atomic symbol for aluminum. So we know we have a metal present. We actually don't have to look any further. We know this is going to be an ionic compound. It's aluminum bromide, but you don't have to worry about that. You just see the aluminum. The second one, Na. What is Na? Well, that's sodium. Sodium you don't think of as being a metal, but it is a metal. So sodium chloride is another ionic compound. Then H2O, good old familiar water. Well, hydrogen gets landed, gets put on the periodic table way far on the left, but if you remember from our discussion and coloring of the table, hydrogen actually is a nonmetal. So we're not starting with a metal. Is the other one a nonmetal? Oxygen also is a nonmetal. So the H2O is a covalent compound. How about carbon dioxide, another very familiar compound? Well, carbon you will find on the nonmetal side. Oxygen you will find on the nonmetal side, so that also is a covalent compound. Magnesium sulfate, Mg, is a metal, so this is going to be an ionic compound. Sulfur and oxygen are nonmetals, but just the presence of that one metal tells you it's an ionic compound. Copper nitrate, of course, copper is a metal, so here's another ionic compound. And then good old familiar glucose C6H12O6. Well, carbon, hydrogen, and oxygen are all are all nonmetals, so this is another covalent compound. So here's the first skill you need in order to move on to naming and writing formulas, is being able to look at that formula, find out, is it ionic because there's a metal present, or a covalent compound, because that makes all the difference in how we do the names and how we write the formulas.